Okay, this is David Zierler, Director of the Caltech Heritage Project. It is Monday, March 7th, 2022. Once again, I'm delighted to be back with Professor Richard Flagan. Rick, once again, it's great to be with you. Thank you for joining me again.
Glad to.
Rick, today I'd like to start with a very topical question before we go back into the historical narrative. We're all watching the unfolding horror happening in the Ukraine right now. As an aerosol scientist, when you look at all of the bombing, all of the fires that are engulfing buildings and tanks and bombings, when you look at the potential of radiation plants or plants that produce radioactive energy, what are some of the things that you're seeing? What are you concerned about right now?
Beyond the just general insanity that's going on, when you see all the fires, you see huge amounts of smoke. That has poses direct risks, though they're trivial by comparison with the other risks that the people in the area are facing. But if you look at the Russians attacking the nuclear power plants, as far as I know, those nuclear power plants are built on the same sort of technology as Chernobyl was, with the graphite used as shielding on them. That's combustible. And if that burns, that can loft huge volumes of radioactivity into the atmosphere. During the Chernobyl accident, I know people who were involved in the investigation of that, people in Finland who were directly downwind, received some of the first signals from Chernobyl, although they did not recognize them at the time. Going back to the era of the Soviet nuclear tests, they had atmospheric conductivity measurements, which were put in place to detect the radioactive fallout from the nuclear tests as a very simple yet sensitive detector of that increased activity. When Chernobyl happened, those sensors started going offline. The signals just went out of bounds. And this caused panic within the Finnish Meteorological Institute that was responsible for manning these stations. They sent people out to tune them, to get them working again, and they went offline again before too long. When the head of the Finnish Meteorological Institute returned from sailing the first weekend that the ice in Helsinki harbor was open, he found his door covered with notes telling him to call the Institute right away. They had seen the first signals from Chernobyl. What happens now? This continued on. The Swedes eventually detected it and recognized it for what it was. They found particles of uranium as large as 7 microns in diameter, collected in filters that had been sampling throughout that period, catching particles that had been lofted up into the sky by those fires. And this is a long ways downwind. With the level of bombardment going on, what happens if those facilities are hit again? if they're hit with the kinds of munitions that are going on? Are we looking at another nuclear disaster? I know that there are other plants of that same vintage around the Eastern Bloc countries and some of the countries that the Soviet Union owed money to, and that was the way they paid them, was by building nuclear power plants, which were built better than the Soviet ones. They actually had good controls in them, but they still have that risk of combustion of the shielding materials. So there's a potential with what's going on of creating a huge environmental disaster long downwind from those facilities.
Have you been involved in creating detector technologies that give us a sense of what's happening right now in Ukraine?
Not directly. I've been involved in creating instruments that measure small particles in the air and have created quite a number of those. And those are used for looking at particulate emissions and particles formed in the atmosphere. But as far as the specifics of what is happening in the Ukraine right at the moment, they're not really that specific. They give you size. The instruments I've created give you size distribution. Some give you an ability to collect samples for subsequent analysis. I've been involved indirectly through collaborators with instruments that do give you real-time chemistry. Mm-hmm. There's a company that has developed and commercialized an aerosol mass spectrometer that we use extensively in our research. We flew the first of those instruments that was sold outside of Aerodyne's own laboratories, sold for outside use. That was part of an Office of Navy Research grant that we had. And while that was being developed under an SBIR grant, Small Business Innovative Research Grant, I was a liaison for ONR with that company, providing technical support in reviewing their progress as the instrument was developed, and in guiding it to the ultimate capability of being something small and light enough that we could fly it for atmospheric measurements. Those instruments are all over Europe and all over the world these days.
So, Rick, it sounds like the bombardment around nuclear reactors in Ukraine right now, this is a massive global concern.
Oh, yes. And it's a very real concern. There's a very real threat that's posed by putting those facilities at risk being disrupted in a major way.
Yeah. All right. Well, let's return to the historical narrative. We're going to pick up in the late 1980s and early 1990s. I wonder if you can talk about some of your work generally in photooxidation at this time, both on the instrument building side and on the capture and analysis side.
Well, that was a period where we had been using an atmospheric chamber. At that point, the chamber we were using was a big, about 60 cubic meter Teflon reactor, basically shaped like a huge pillow. It was installed up on the roof of the Keck laboratory, used ambient sunlight for the illumination, for driving the photochemistry. I think we were still using that at that point. We had a lot of the instruments that we were using were commercial instruments. They had some serious problems. The key instrument for measuring the small particles was something called an electrical aerosol analyzer, which would get a measure that was representative of the number of particles larger than a given size. And it would step through sizes and take differences between two successive measurements in order to get the concentration within a given interval. It was doing this during an experiment where that entire size distribution is changing continuously with time. And often where the number of concentrations were low enough that the readings were quite noisy. That noise would sometimes give you negative numbers. We don't have negative particles. So we had a lot of trouble with analyzing the data. And my students were doing some really creative work trying to extract best estimates of the size distribution coming out of those experiments. But the data were really inferior. I was teaching a course at that time on aerosol measurements, on atmospheric measurements in general. At the time, I was teaching about, at one particular moment, I was teaching about the measurement of the particles. And as I was preparing I would each week give one lecture talking about an instrument, sort of dissecting it, walking through how it worked, good parts and the bad parts, trying to help the students understand the tools with which they were working and to get ideas on how to take them in new dimensions. And as I was preparing the lecture on an instrument I really didn't like, I started thinking about some of the other instruments that we were working with, some of the mass spectrometry that we were doing, trying to get the chemistry on the particles. And started to wonder, we had an instrument that was a calibration tool. What it would do is separate particles in a narrow interval of sizes as they flow through a long coaxial, a cylinder inside a tube, electrostatic separator. Charged particles would migrate across the particle-free sheath gas as they were carried downstream in this instrument, be taken out at a downstream point. We would step the voltage if we wanted to make a size distribution, and that would take 20 or 30 minutes to do a decent job of capturing the size distribution. It was way too slow for the experiments we had. Sometimes the action was over in 10 minutes. Thinking about that, started asking the question, what would happen if we changed its mode of operation? If instead of classifying the particles in a steady flow, steady electric field, and then stepping, what would happen if we classified them in a time-varying field and just continuously counted into time bins? And rather than work on the lecture I was supposed to be preparing, I did the thought experiment, the zeroth order approximation of the instrument, and derived a model of it, and looked at what its response function would be. And for this simple model that I had developed, that pointed to a new instrument. Because what I got was the same answer that we got with the stepping mode. Some different constants, but it was basically the identical result. The next day, I gave the students a lecture on an instrument that didn't exist. I showed them how we could take this classifier, this calibrate tool we could only use as calibration because it was so slow, and turn it into an instrument that would be fast enough to make the measurements. That was an interesting start, but all it took was a computer program to translate that calibration tool into the instrument that we needed. And so 2 weeks later, we had the first version of that instrument working, and my students used it in the lab course. The student who had defended her thesis, whose frustration led me to this, later asked me, "Why did you wait till after I finished to get this done?" That instrument, it went through quite a few variations. When I sent the paper out for review, I got a very elegant, it was something like a dozen pages, handwritten notes showing me a major improvement of it. The improvement was something that we immediately adopted from the notes and initials that were on the paper, on the pages of notes. I was able to identify who the reviewer was and asked whether he would want to be a co-author on the paper, which he declined.
That's great.
But it was one of those beautiful reviews.
And Rick, that
was the first one.
When we talk about photooxidation, does this have both an industrial and a naturally occurring context?
It certainly has a major naturally occurring context, the photochemistry that we're looking at in the atmosphere. I have not looked explicitly at the industrial applications of photochemistry. I know they exist, but I don't know the details of them. I've focused much more on what's happening in the atmosphere.
Mm-hmm, mm-hmm. I'm curious if you became involved at all in the aftermath of the Exxon Valdez disaster. Was there an atmospheric dimension to this at all?
That one, I was not involved in at all. And I don't recall nearly as much of a discussion of the atmospheric context as in the Gulf of Mexico disaster decades later.
Deepwater Horizon.
Deepwater Horizon.
What might be the difference?
But there you had a huge fire as well.
Right, right. So is that to say that generally oil spills are contained in the water and land? They don't find their way into the atmosphere?
No. That depending upon the oil, there are different amounts of volatile components. Methane is one obvious part of it. That was the fire in the Deepwater Horizon, at least the initial significant initial part of it. It was definitely a concern. The volatile components will evaporate, and once they evaporate into the atmosphere, they can undergo that photochemistry.
I wonder if you can talk a little bit about Raman scattering techniques and how they were relevant for your research.
We did some work trying to get to basics of chemistry going on inside particles. We did some work using a modern version of the Fletcher-Millikan oil drop experiment, which involves levitating a charged particle in an electric field. In the original experiment, in Millikan's original experiment, was just two flat plates. His very creative graduate student, Harvey Fletcher, found a way to electrostatically nudge a particle back to the center of his view volume if it started to drift too far out of that. And that was one of the keys to the experiments that gets missed in most of the discussions. He was also the guy who came up with the use of oil rather than water,
right,
so they don't evaporate. We used that to look at what was going on within the solution droplet. We could levitate a charged droplet, and we could hold it for an extended period of time. And with that droplet levitated, we could then measure the change in mass with time as an indication of the increase of amount of material dissolved within it due to reactions of gaseous species diffusing into it. But it would be much nicer to be able to probe the chemistry going on within the droplet itself. And we actually used two different optical techniques to probe what was happening within the particle. The first that we used was a Fourier transform infrared spectroscopy, where the small absorption that was occurring would actually heat up the droplet by a very small amount, thousandths of a degree Kelvin. But that would cause enough of a size shift by evaporated water that looking at optical resonances in the angular scattering pattern, we could detect absorption. That worked, but it was very tedious, very slow. We had a later student who tried using Raman spectroscopy. And he was, in fact, able to probe the absorption with Raman spectroscopy by looking at the shifts in the scattering pattern from that levitated droplet. Data analysis from those experiments was very complicated because we had to deal with all of those optical resonances within the small particle. It was not something that we pursued a lot after that initial effort, but it led to a very, very nice thesis for Chak Chan, and he went on to use it in other methods extensively in his career when he moved back to Hong Kong after finishing with us.
Have these techniques been relevant for more recent work, or are they sort of bounded in a particular chronological time for your work?
We've used the levitation technique at many points along the way. The first experiments were just looking at the thermodynamics of solutions. What happens if we take a solution droplet, and dry it out? If we lower the relative humidity it's exposed to, it will shrink and dry, but it won't necessarily crystallize at the point where thermodynamics tells you it should, because the nucleation of a new phase provides a kinetic constraint against getting to that full equilibrium state. So we could actually measure the water activity over the solution droplet, going into extremely supersaturated solutions. And this happens in the atmosphere. It's directly relevant to the atmosphere, that in that drying process, you can go into that supersaturated state, keeping the droplets wet and much larger than they would be after they dried out. So that occurs in the atmosphere on a morning after a fog. You will see as the sun rises, the temperature rises, the fog disappears as fog, but it still seems hazy for a long time. due to those droplets remaining wet. So it is a factor in the haze following foggy days. Mm-hmm. It's an important part of understanding the atmospheric, not just visual range, visibility, but also in the context of climate change, how that haze is scattering sunlight back to space. And it's part of the uncertainty and the large source of uncertainty in radiative scattering. Mm-hmm. Mm-hmm. In modeling of the energy balance for the planet. Mm-hmm. The levitation we've used also to look at that crystallization that occurs, to probe the kinetics of the crystallization. And that has gone beyond looking at the atmosphere. In a project that I did with Julie Cornfield, she got me interested in the question of how polymers crystallize. We looked for homogeneous nucleation in polymer solutions. And this was much later. This was more like Adam Olson finished his thesis in about 2005 or 2006. What we did was we would levitate a small polymer particle, and then we would cycle it through increasing relative humidity and then decreasing relative humidity, and measure the humidity at which you would get the solid deliquescing and becoming a solution droplet. And then we would see those optical resonances. Then when we would dry it, it would eventually crystallize. We were looking for a stochastic, a statistical process, but we found systematic variations. What happened in one experiment depended upon what had happened in the previous experiment. We would see changes, systematic changes, as we went through a sawtooth in relative humidity. Ultimately, we had to look at the crystallization very differently than we had before, and realized that we could explain this in terms of entanglement of the polymer molecules that was persisting, even though the polymer was seemingly fully solvated, fully in solution.
Rick, I'm curious, your collaboration with Aaron Rulison, ablation of silicate particles, was that part of a larger endeavor on non-terrestrial research, or was that more of a one-off project?
Well, that was a key part of his thesis.
Uh-huh.
Tom Ahrens was professor of geophysics, was looking at questions that related to the extinction of the dinosaurs. Yeah. Major impact, spewing huge amounts of material up into the upper atmosphere that darkened Earth for a long time. And from that came the question, not of these huge objects coming into the atmosphere, but of smaller ones. If you have a really small piece of rock entering the atmosphere, what happens to it? That project actually came out of a term project in my aerosol physics course that I posed for a student who I knew had a strong interest in astronomy. He had built his own telescope. He was a very avid amateur astronomer studying in chemical engineering. And I knew he would be interested in this. Tom had been asking me questions about this. So I had him look at the theory of what happens when a small rock comes into the atmosphere. And he dug through the literature and came up with major flaws in the physics of the models that were commonly used to describe how a meteorite behaves in the atmosphere. Basically, they assumed that the drag constant, the proportionality from velocity to drag force for a particle coming into the atmosphere is constant as it goes through a regime of the atmosphere where it has to vary a lot, where the velocities are immense, coming in at velocities of many kilometers per second and decelerating down to velocities where simple fluid mechanics would describe what's going on very well. So the model he came up with said that the particles had to heat up, but ultimately they'd start to melt. And once they melt, then you have strong shear forces, and liquid would spall off just due to aerodynamic drag. And so this called into question a number of aspects of what would happen when an object enters the atmosphere. Tom Arons was very interested in this, proposed that we used a large apparatus that he used for looking at major impacts. It was basically a large gun that would shoot a projectile at a surface and measure what happens to the rocks that it hits. But we used that as a way to inject small particles into a gas and then look at those small particles. We started out looking at the system here at Caltech, ultimately used a larger facility up at NASA Ames to measure what happens when small particles of known composition enter into a stagnant gas, undergo this very rapid deceleration. What temperatures do they reach? How long are they visible as hot glowing objects? And what's the nature of the particles that are left behind? And so it led to a very different model for meteorite entry into the atmosphere than what was commonly used at the time.
Was JPL a factor in this research at all?
Not from our involvement. They may have been involved with Tom, but we were looking at one small piece of the puzzle at that time.
Rick, an overall public policy and perceptions question. So if today we can understand that there's widespread public appreciation that coal, even unique among the fossil fuels, is dirty, both in terms of its potency in creating carbon emissions and as an air pollutant, when did this shift in public perception come about? And what was some of your research that might have contributed to this shift in perception?
The shift was coming about when I arrived here.
That early?
It had started much earlier than that. There were some major air pollution episodes back when I was far too young to be doing any science that really caught the world's attention. There was an air pollution episode in 1952, I believe, in London, that over the course of about a week killed about 5,000 more people than would have died during that same period without that episode. It was a statistically significant perturbation on the death rate. And that was clearly linked to the air pollution in London, where a lot of coal was burned, not just for power generation, but also for space heating. So in small, very inefficient furnaces and houses. That awareness was out there from that time, and and long before. The first air pollution laws date back into very early in England's development, where it was recognized that coal was a major problem. That's always been part of coal, that recognition. When I interviewed at Caltech, I was actually introduced to that question specifically with regard to some aspects of the coal combustion by a then professor of environmental engineering science, as the program was called at the time, and chemical engineering, Sheldon Friedlander. And he sort of posed the question that in urban centers at that time, the aerosol is enriched with heavy metals. Why? Where does it come from? Why are those particles so abundant in the atmosphere, well beyond the natural abundance in the area? And so the first project that I started when I came to Caltech was looking at what happens to the mineral matter in coal when coal is burnt. And coal typically contains several to 10 or more percent of mineral matter by mass. We built a laboratory combustor to explore that, where we would burn on the order of a kilogram of coal per hour. So from the point of view of coal combustion, very small. From the point of view of typical laboratory experiments, rather large. But it allowed us to look at the nature of the particle generation. Even before I did that, I had done some modeling. The first thing I did was on that problem was to just read vast amounts of literature to the point that I wrote a review paper on it. And in doing that, I found strong hints that mineral was being vaporized during combustion. And so we built an experiment to test that. And with that, we measured the size distribution and got size distributions that were close to what I had predicted with a very simplistic model at the time. But we also used some samplers that I had developed to collect size fractionated samples of particles down to quite small sizes. And those, we found ways, using tools of the geologists, to look at the distribution of the mineral content among those different size fractions. And, that was my first venture into the area. The broader recognition of the problem came out of a number of environmental episodes. Those extreme air pollution events, they led to solutions, reducing the use of raw coal for space heating to go to somewhat cleaner fuels, building tall smokestacks to make sure that the air pollution isn't released right at ground level. That became a key part in the acid rain problem, exporting the large amounts of sulfur and particulate matter into the atmosphere high enough that it could be transported long distances before it would come down in downwind locations. So there's been a continuous evolution recognizing the contributions of coal to air pollution, air quality, and climate change. experiments we're doing now are showing that the sulfur released by coal combustion has drastically altered how particles form in the atmosphere. And so in the modern world, the clouds that we see, which form on seeds that are the smaller particles in the atmosphere, those seeds are different. So the clouds are formed in different ways, perturbed by man's action through the burning of coal and other fossil fuels. This is in addition to the effects of the greenhouse gases, which is the driving force behind the general warming of climate. Part of the reason this has been slow to be identified has been that the particles that have been perturbing the atmosphere led to a cooling effect, reflecting sunlight back to space and counteracting some of the global warming that's been building over time.
Rick, given how far back these problems go, are you surprised just how prevalent burning coal remains in the world economy?
Given human nature, unfortunately, I wish I were. I wish I had grounds to be. If you're trying to build large industrial systems, if you want to process huge amounts of steel, burning coal is a convenient way to do it. Plus, you want to add carbon to the iron to make quality steel. So the operations for that industry, coal is fairly natural. For building power plants, it's a very dense fuel, has a lot of energy release capability. So it became recognized as an important fuel very early on. The early steam engines used wood, but coal turns out where it's available to be a more convenient source. The ease of use of these resources is, it's very, very tempting, and people succumb to that temptation. They did not recognize that the dangers that were being created in the process.
Rick, just a nomenclature question. What are aerosol agglomerates?
Okay, so when you start with very, very small particles, a good example would be diesel soot. So diesel soot is produced by gas phase reactions in fuel-rich regions of a flame that start building up bigger hydrocarbons from smaller ones. They form aromatic rings and ultimately form tiny particles that, as we see, are black. The size of those little tiny particles that form start out as molecules, and they grow up to a couple of tens of nanometers in size. But they're produced in huge number concentrations, and they undergo Brownian motion in the air and, on occasion, collide with one another. And they'll stick stick together, initially probably by van der Waals forces. But as they're forming, additional material is coming out of the gas phase and deposits on their surfaces and grows them up to larger and larger sizes. But the rate at which these little spheroids come together and stick is so great that the amount of material coming from the gas phase can't completely coat it and make a nice uniform sphere. They form aggregates of particles that are ramified, is a common word to use them. It's not like a cluster of grapes. They're more string-like, fractal-like aggregates that aerodynamically will look quite small, but physically will become quite large.
I'd like to talk about your work with journals and open access, but as context to that, tell me about your service on the library committee at Caltech. How far back does that go?
My first introduction to the library committee came when I arrived at Caltech. At that time in the Caltech library history, Caltech had a whole bunch of small libraries. The one large central library, but a large number of satellite libraries. There was one in environmental engineering. And I was constantly in there digging through the literature.
This is pre-internet, of course, when people actually went to the library to find things.
Precisely. And, the first challenge that I was given, that I took on, was this review that I did on particle formation and coal combustion, which had me going to libraries all over campus to find the different kinds of information to pull all the pieces together. So I would sometimes visit 10 or 11 libraries in a day. I was asked if I would be willing to serve as environmental engineering's representative for libraries, which I agreed to. And from that was on the library committee for many years. At Caltech libraries were a very, very special place. They were scattered. It was not very efficient to go to all of them. And we didn't have all the journals. Caltech is a small place, and when you start going into fields that have not been represented at a small institution, you discover gaps in what they have. And one of the important things that Caltech had done that was very creative was to set up a document delivery system where if you found a reference that you needed access to, there was a little slip in the library, you could fill it out. And then a few days or a week later, you would get a Xerox of the paper in the campus mail. And that was very convenient. It was done at so many cents per page. And we used it a lot. We went through a number of transitions in the library. One was the use of this document delivery system was becoming so large that the library director, university librarian, concluded that it was not practical to keep counting the numbers of pages that were being scanned. And he proposed at one point that what we should do is just have a fixed charge for a copy. And that was set at a reasonable amount so that people wouldn't object to it too much, and it continued to work well. But following the period of very high inflation in the late 70s, the commercial publishers learned a very important lesson, and a lesson that they have been profiting from to this day. And that is that the use of scientific journals is very inelastic. That is, if they raise the price, the number of subscriptions does not go down, or does not go down easily. What's going on? Well, it's the university library that pays the price for the subscription, and it's the scientist who's not paying that price directly who demands that we have the journal. And so it was actually at the time when this discussion of changing the pricing structure occurred. As that occurred, there were no. Trying to recall exactly what the sequence was. In fact, it was the driving force for the pricing structure. The journal publishers were escalating the price at many times the inflation rate. Sometimes 20, 30% per year. Huge escalations in the subscription price because they had a captive audience. The librarians were stopped from canceling the journals because the faculty demanded that they have access to the scholarship in their field. The proposal made by the then university librarian was that as we changed this, it was dealing with the numbers of subscriptions. How do we cancel subscriptions? So we're going to have to cancel subscriptions. The cost is going far beyond what we can pay. How do we choose what to cancel? And as that was discussed, you look at the journals, you see which journals are not being used very effectively or not being used very frequently. And yet cost a lot. Okay, those are the ones you cancel. Well, then what do you do with the document delivery? And the first proposal, which was from the then university librarian, was, well, we canceled the subscription. We'll have to charge the faculty for the interlibrary loan to get access to those articles. That original document delivery was even for journals in the Caltech collection. You could request an article without having to physically go to the library. And then you just get it in a day or two. As you start canceling, then you say, okay, we've got to go outside and get it. Well, the researchers should pay it out of their research grant. And my response to that was, if we do that, nobody's going to willingly let a journal be canceled. If we want to deal with the budgetary question, we have to think about the faculty, the research that's going on here. and make it practical for people to allow journals to be canceled. So ultimately, that was the driving force that switched to a fixed cost per article that was the same whether we had the article on campus or not. Again, this is pre-internet. So if you wanted to physically make your own copy, you could walk to the library and not pay that fee. You just pay the per page cost of copying. But if you wanted to have someone else do it and deliver it to you, you paid for it. Well, this expanded that outside, all at a constant rate. Following that, the library was able to not fully meet its budget because the escalation was still going on. But we actually had faculty saying, we were showing faculty the prices. They would see what the price was for the journal and how often they used it. They'd say, you can cancel this journal because it was practical for them to do it. So I was on the library committee for a long time through this extended period where we were having to cancel large numbers of journals every single year.
Rick, did those discussions get to the existential level where there may have been discussions about whether Caltech even needed to maintain a library?
We had one provost who said, well, first question came with books because it was cutting into the purchases of books. We had one provost who argued, Caltech faculty don't read books, they write them. And that didn't get to the point that says, who is it who actually reads books? It's mostly students, and no, they don't write the books. But that was a starting salvo into the question of whether we need a library. We clearly needed access to the literature and the access to the main journals for the fields where there are large numbers of people going at regularly using the same key journals. That was not going to change easily. For the smaller disciplines, the effect was much more direct when you start canceling. So canceling, physical review, the ACS, Journal of American Chemical Society, Cell, and so on. Those you're not going to cancel. Someone's got to bring those onto campus and make them available. But the journals that are used by a small number of research groups, those were prime targets. As the internet developed and as electronic forms of access to journals developed, then there came increasing questions. How many journals do we need to have access to?
What was the outcome of that discussion?
Yeah. Outcome, at one point, Steve Coonan, then provost, said, okay, we should have a true accounting of who uses what journals. How much are our journals used? So he took the approach of he pressured the library to do a survey for every faculty member. What journals have you published in the last 5 years? And what journals have you cited? And that would define the set of journals that we need to consider at all. Well, first, that's a huge burden. Maybe not for people who work in a relatively well-defined, well-constrained discipline, but people who cross boundaries became a huge exercise. There was pressure to rely on electronic access as opposed to having physical library was one outcome from that. That survey brought attention to these questions of what journals we need. There were faculty who listed hundreds of journals that they used. And so the answer was not so easy. This was also a time when there were growing pressures, growing interest in developing the internet into a mode of communication. In physics, which is where our provost at the time came from, there was Archive, which had been set up at Los Alamos as a preprint server for the physics community. And so there was a way to get access to the articles even without subscriptions. Why can't we have that in all fields? Why do we need these journals? We looked, the library was looking at modes of using preprint servers, of providing access to material that went beyond the journals. Things like digitizing the Caltech theses to make those available. And there were a few ventures aimed at making fully electronic open access journals. There was one headed out of economics that got a lot of attention at the time. In discussing all of this, reading what was in the literature and discussions with publishers when they were not responsive to our pleas that their escalation of journal prices was just not sustainable. The question of how we should respond to this journal crisis really came to the fore. In one of many meetings with the then university librarian Ann Buck and I, with Steve Koonin, the provost, where he was arguing for huge cuts in the library budget, huge cuts in the subscription budget. The idea came out of, let's get together people in the community, not the publishers, but rather the users. So the universities, the libraries, maybe some society publishers that are well behaved in the pricing game. And let's have a serious discussion about what would be the best way to use the electronic media. And so Ann Buck and I organized a conference. The conference occurred, I believe it was in 1997. It was a conference on scholarly communication.
And this was an international conference. This went well beyond Pasadena.
It went well beyond Pasadena. It was small, but we invited speakers we invited participants from universities in the US and in Europe. Did not cover the whole world. We organized a conference that was to be a workshop to come up with some proposals as to how we might better use the internet. This conference on scholarly communication, we had a total of 4 speakers. Each of them presented a vantage point on publishing, both on publishing and on the needs for publishing. We had quite a number of library people from around the country and some from Europe. We had a number of academics, and we had provosts from 7 or 8 major research universities in the US. The provosts were a very important group. They're the people who pay the bills. And so we wanted to try to get the whole spectrum of viewpoints for how publication fits into the academic setting. I'd have to dig back to remember all of the speakers. The most eloquent one on the question of why we need to develop open access journals was a professor of theology from the UK. His specialty was Christianity in the 2nd century, a field in which there was one journal. That journal was a very glossy sort of journal that wealthy people might subscribe to and have on their coffee table. In that field, it took about 7 years from the time that an article was accepted until it was published. And he was a very eloquent spokesman for why there was a need for a different mode of publication where you weren't constrained in the same way by producing a showy document that would satisfy the coffee table mode of publication. We had one presentation each day. The rest of the time was all spent breaking up into groups and discussing what is the problem and coming up with proposals for what is the solution. Most of the panels that we set up had representatives from all of the different groups that were represented at the conference. But one was distinct. One was all the provosts, the people who pay the bills. And for a week, we had serious discussions. The last day, each of the panels presented their proposal for how we would do things and then synthesize that into an overall proposal. That proposal is published on the Caltech Library website. It's entitled Scholars Forum. it was one that recognized that the value in journals. What is the value of the journal? Well, first, who benefits from a journal article most? The primary beneficiary is the author. And the secondary beneficiary is the university.
Because it gains some of the prestige that's garnered on the author.
That is correct. The university builds, it's got a portfolio of contributors that build its reputation for what it does in research, in scholarship in general.
Rick, maybe it's a naive question, but what about the readers? Wouldn't they stand to be the primary beneficiaries of a journal article?
So what is the author buying with their labor that they've devoted into the object that goes to the journal?
The educational betterment of the readers.
Eyeballs. What the author wants most is readers. They want lots and lots of people to read their work. And so they select where they publish according to who the readers are, how many there will be, is it getting to the right audience? Now, if you look then at who is paying the bills, it's the library. The subscription rates that libraries pay are far higher than the subscription rates that an individual would pay for a journal. And many people don't have access to journals. I look around the country, around the world, there are lots of small companies that don't have access to the journals unless they find some backdoor in through a library. So a proposal was made. Now, we should have journals. The journals should be open access. Who should own the copyright? The author. What does the journal need? The journal needs a perpetual license to publish that piece of work. So when the author submits it, they grant a license to publish. And that license should not be revocable. You'd like that material to remain available long term. But the author should also be able to post it on their own website. The question of how you process this is very important. Why do authors publish in a journal in the first place? Well, it's because that venue is recognized by the readers as being significant for their particular research, for the author's particular research. But what is the value added by the journal? Is it the glossy presentation? Maybe. But the real value is in the vetting of the article. It's in the certification that this piece of work has met the standards of the field.
You're saying peer review is a unique aspect of journal publication.
Peer review is the central aspect of scholarly journals. That there is a vetting, a certification function that the journals provide that is the biggest value of the journal. Now, how is that provided? Well, there's an editor for the journal who for large journals will typically be paid. For journals like Nature or Science, are paid quite well. Those are professional editors. For many scholarly journals, the editors, if they're being paid a pittance compared to what their time is worth and what the time they spend on a journal is. I have edited a journal. I received zero compensation for my efforts, zero financial compensation. I received compensation in terms of recognition from my colleagues, in terms of things I learned in the process, but I was not paid for that. So we have an imbalance. If we create open access journals, how do we pay for it? How much do we pay for it? The real value is in the reviewing. That's done almost entirely by volunteers. Reviewers are not paid for their efforts. The publishers, there have been many surveys over the years that show that scholarly publication is the most profitable, or one of the most profitable, highest return on investment industries out there. I have seen articles in one case by the then president of Elsevier saying, let's do an analysis on what is the value of an article, and going through all the different costs, the research, the equipment, the graduate students, the postdocs, the faculty time, all that went into writing it. And then the editing, well, claiming large credit for that. Well, the editorial function, the function of the chief editor, the person who's sending it out to reviewers and then passing judgment on the reviews. There is a technical editing component, which is a real cost, but varies highly from author to author, article to article, depending upon how well the person writes and how much attention they pay to their writing for the particular submission. One might assume that the cost of that technical editing might reasonably be a cost for the author. But if they spent more time getting it into the proper format, on critically evaluating their writing, there would be less technical editing required. One could think through all of the different processes involved. One of the proposals that came out was that we ought to use things like archive, the internet repositories for articles, have authors submit there, and maybe editorial boards, editors should select from their articles that they then want to go through the additional effort of having reviews, but you could have public reviews submitted. One could come up with very different models that are totally different than what we have now, which is electronic versions of print journals, many of which are designed to ensure that they have a high enough print component that for the libraries to have access to it, to everything, they have to make sure there's enough that's not available electronically to demand a subscription. because once it's available open access, anyone can get to it. There are many different ways we can look at it. A lot of what is done right now is you have commercial publishers double dipping. That is, they charge high subscription fees, which the libraries are paying. They charge fees to authors if they want to make it available open access so everybody can see it. So they get paid for the same article twice. This is a really critical issue for academia now and in the future. We did try to get this discussed at a higher level. We tried to get it discussed by associations of universities, associations of university presidents. And somehow it always took a lower standing than what it really deserves and what universities need.
Well, Rick, last question for today. 25 years out, when you started thinking about these things, in light of the ubiquity of the internet, and maybe even specifically social media and the way that online analytics give a much more precise sense of readership or eyeballs, as you say, how have these issues changed since the late 1990s, and how have they remained the same despite these technological progressions?
There were some major ventures in creating open access journals. PLOS, Public Library of Science, being a prime one. That started out with a view that they were going to compete head-on with Science and Nature. They were going to have the feature articles, the other expensive components that require high-level professional labor to make them work. And they set a price. The commercial publishers are very savvy, and they took the very high price required to put all of those very expensive contributions into the journal. They took the high price that came out of that and said, oh, well, this is what you would have for a totally open system. No profit. We'll take that as a floor and raise the prices above that. What we've had happen is that the commercial publishers have monetized open access quite effectively and work very hard to make the case that they are required. My sense is we don't need them anymore. That societies can handle the challenge of electronic publication. The machinery exists. There are open access versions of very, very effective software to run a journal. If you wanted to set one up, you could do a quite credible job in a few days with software that you do not have to purchase. You might find it advisable to get someone involved who's used it before to assist you in getting started. But you don't have to do like PLOS did and hire a big software company to build it and then leave the ownership of the software in the hands of that company so that they can hold you over the coals in the future. That original software didn't work very well and they replaced it. So I don't know exactly what the status is now, but I think we've come a long ways, but we haven't come a long ways in terms of true open access.
What would that look like? What would true open access look like? in a way that would be economically viable for all interested parties?
Well, first, you have to define what is a fair return on investment, and you have to constrain the return on investment to a fair level. 40% return on investment is not a fair level. I think there's a real place for professional societies. A lot of the journals come out of professional societies. Right now, there are many supposedly open access journals being started that are predatory journals, that are companies that are set up to extract money from the community, not to provide a valuable service. Societies could set up journals. There are costs, and there are services required that have to be paid for. The fees that are charged for the open access, for the publication charges, author publication charges, as they're called, those are needed and have to cover the real cost, but again, within reason. They don't have to cover luxurious office headquarters for a large company in some expensive city. You might see journals that look very much like they are today. But one could also ask the question, can we do something with the reprints? I think COVID has shown us very clear the value of these preprint archives. The Met Archive has had huge attention over the last 2 years because that's where a lot of work was being published long before it was considered for publication in the regular journals. Are there ways to use that to provide the vetting, the certification that's needed in a way that guarantees that you are getting good reviews? There are journals out there that I think do a very good job of at least one form of that. There's one set of journals that I publish in fairly frequently that is run out of the European Geophysical Union, that are open access journals. Instead of having a few editors, each of whom is handling hundreds of papers, they have a large number of editors, each of whom handles a small number a year. They will ask for a couple of anonymous reviews where someone takes on the challenge of providing a critical evaluation of a manuscript. But they open up the review process so that others in the community can provide a review, a signed review, and those reviews become part of the archive along with the author's response to them. And they have a discussions journal, which is where the first submissions go in. And then they have the regular journal, which is where those that have been accepted for it reside. But both are continuously available. So things that have gone into discussions are available as in the preprint servers, even if they're not accepted. And the final version is available, but the original submitted versions are. There are very different models that can come out. And I think we need to be trying more of that.
And Rick, obviously there's a generational question here, because for better or worse, for graduate students, for postdocs looking to make a name for themselves in an academic setting, journal publications is still the golden standard for hiring decisions, for tenure considerations. So this is really an issue of ongoing major import.
That's where having a framework, as the EGU has done with a number of different journals, having a framework that can gain credibility for providing that critical certification role is very important. There are also a huge number of predatory journals out there that provide none of that, that they allow you to have a line on your CV, but nothing more. The articles are available. Are they any good? Yeah. How many authors will bother to read something that's published in a place that's known as a very suspect forum? These are issues that I think are going to remain, and this is part of the challenge that the internet age provides us.
Well, Rick, on that note, we'll pick up for next time. More work in the 1990s, and then we'll move into the new century.